especially low for amplifier. Anybody can fully
ये क्वेश्चन तो सर यहाँ पे मैं देखा कमेंट्स
Hello, good afternoon. Good afternoon, viewers. नहीं. You can share that if you have any questions.
बोल रहे हैं कि बस
Any questions? Just ask any questions.
मैं तो बोल दिया सर माइक सर पे है क्या माइक
Mic to high level.
we start with some questions
Unless ask to get some question from them.
हाँ वो तो पूछा था
Okay. No.
उसके बारे में बता दीजिए आप
Can be. मेरे को मिल जाएगा. Essentially, this session, we wanted to answer some of your questions if you have. That is number one. And if required, solve even a problem or two if you have if you have some questions related to that. If you have some questions, we'd like to answer that first. First, we'd like to answer if you have some questions. Any question coming by? Any question if you have tried to solve some of those assignments and preparing for the final exam? If you have some questions, we'd like to answer them because there are a lot of numericals in this course. It's numerical oriented. Two questions, of course, we saw in the comments. One of them was, what is the scope of green building in India? Well, the scope is very much there. There are professionals who are practicing green building, rating and as well as they're basically using some softwares, maybe design also. Yes, some people might be trying to do design, but largely intuitively. So the whole idea of this course is that you don't prepare to do things intuitively, rather you look into the basic physics behind that and try to do it. So that's related to green building. And the other aspects is, of course, the lighting and acoustic design. Now, that's of course, if you're a, if you do a job, for example, noise control, there are a lot of work being done. Sometimes, I mean, I myself have been doing a number of consultancies related to, sometimes related to, turbine generator noise, because there are there is maximum level of dB outside the boundary of the power plant is fixed, or even outside the turbine generator house that's been fixed. So one would like to find that out. Similarly, for some cases related to some electrical transformer noise and so on. So noise is also one of them. There is a case not with me, but somebody else having generally the noise from the aircraft landing in Delhi airport. So there are issues related to noise, and also, as I said, the issue related to green building and things like that. And lastly, of course, the daylighting. This is related again. It also goes together with energy efficient building design. Now, a lot of people use software to do that. Now, unless you know the basic fundamentals, and using software like a black box is not the best thing. So that was the idea about answer to the two queries that have been put on sometime as comments.
One is finding the acoustic transmission of a straw board.
Well, finding I mean the value, or I'm not sure value will be what value. One can look from net or even from some books. Straw board, one can look into literature to find out. I'm not sure in the Indian Standard Code, where are the code 49 something, 29 or some such thing, noise abatements in buildings. That will give some values for something. So straw board, I'm not sure what the value, but how to find this out, because straw board is depending upon what is the frequency that you are looking at. Measurement is one thing that can be done, but there are very few laboratories which can actually do it, because it needs special isolation, acoustic isolation of the laboratories. So it has to have NPL can do it perhaps. Similarly, CBRI has some facility. So finding is not you may not find it everywhere, and that is what it is. But values you might find such in the net, you might be able to find it out. Straw board, depending upon what is mass, but there will be some absorption in there, because straw board would absorb. So transmission loss is one thing, absorption coefficient will be another thing. And if you are looking for absorption coefficient, average, NRC, noise reduction coefficient, or whatever it is, that values, absorption values, I think is available also in the auditorium code for some of these materials. I think it is 2526. 25.
What's it?
What is the code? 2526 in the acoustic design of auditorium.
I think so.
2526 is the code. So there we go.
Somebody is asking how can I relate this course to Vastu Shastra?
Well, I mean, Vastu is something I am not, I cannot answer, because it is not scientific. To my understanding, if it is based on belief that you put your pillow in a given day side, your life will change. So that cannot be related. But traditional Indian design, Indian practices, or practices in a given country, any country for this matter, traditional practice, they have been based on empiricity. People have developed practice. For example, like you don't make a house, west-facing house, or long axis should be parallel to mostly like south, north-south, spanning along north-south direction. So that south is one of the good orientation in this country, because we belong from 8 to around 32, 33 degree latitude, and there Now, the long axis should be parallel to north-south direction. Am I right? Yeah. So that's what my friends also say. And by calculation also you'll see that. So that has been practiced by people. And also if you see traditional houses in Kerala, they will differ quite, a bit from that the houses in, let us say, in Jalandhar, Punjab, or Rajasthan, because the climates are different. So construction materials, they'll be different. There'll be hardly, you won't find too many gable roofs house in northern India, because the rainfall is much less. So traditional practices have been very, very good. Vastu, I don't know anything. And I personally, realize that changing direction of my house is not going to change my life or my so-called fortune or something like that. So therefore, that relationship is not available. But you can always, whatever you feel good, you can analyze it using the physics behind.
They are asking that in green building concept, what would be the noise cancellation principle?
Well, actually, in the green building concept, I do not think there's too much of a noise. The noise issue is not being covered too much. But you want to incorporate it, you can always incorporate it, right? So I'm not very sure in green rating is there anything related to noise control. But first thing is when you are planning a building for noise, very first thing is that you should keep the noise sensitive areas of the building away from the noise generating, maybe the highway or something. The distance is one of the things, and direction is also an important thing. So, this is external noise control into the building. Then you can of course use some sort of absorbers, some sort of absorbers, which was this one. For example, if you have a sunshade, right? If you have a sunshade, then if you have a sunshade or something like that, you can put absorbers here. So any sound coming in, you get reflected and then enter. So if this is an absorber, then like this is, if I is the intensity received here, so this will be simply I0 if I go. It will be I0 multiplied by the absorption coefficient of this absorber. So it could be simply putting something like gunny bag pieces or straw or similar sort of thing, or decorative, some sort of absorbing material one can put. Besides, the distance is the main thing, because you remember we talked about SPL is equals to PWL plus DI minus 20 log R minus 11. So distance is very important. External noise control is good, but I do not think in the green building concept there is a maximum value of the noise level. Right? Green ratings and all. Any question coming?
So in case of room resonance, what will be the real scenario is asking?
Okay.
How to find NX, NY, and Z?
Okay. In case of in case of how do you erase it? Erase.
Then erase it. The right side and the right arm, no? This one is there.
Okay. Erase everything. Okay. See this. Okay, now this goes to the pen. Now basically, if this is the room and its dimensions are something like this, right? Okay, just a minute. So if the formula is actually, we gave some formulae. If you have seen, there was a formula given. So NX, NY, and is now sharing?
Yeah, it's sharing.
Okay. So, right, something like this. what you're saying. Not this. Okay, maybe it's, no, this. Let me raise it out. It's right. Something like this is fine. So there's a little pen. This is sharing now. Okay, okay. So this is the room. Vertical. This is something like that. Okay, this is something like the room. Now, there can be resonance along this direction, as well as, if the source is somewhere up there, so there can be resonance along this direction, y-axis, as well as vertical direction, or combination along the diagonal. So, nx, ny, nz are simple integers, right? So, nx, ny, nz are simple integers. So, for value, you trial, just put this nx value equals to 0, ny is equals to, the formula was nx, formula was
f is equal to
f is equals to c by 2 under root nx by a. Yes, let me again use the eraser. Nx by a square, whole thing, right?
in the class.
Yeah, this was square actually. Ny by b square, because otherwise the under root will not come. Nz by plus nz by t square. So, this is nx. Now, you put this equals to 0, this equals to 1, this equals to 0, then you get in vertical direction. I mean, y direction, whatever is the y direction. You put this equals to 0, this equals to 0, this equals to 1, then you get the frequency at which the resonance will take place, right? Frequency, because velocity of sound is the frequency at which. So if you know your frequency, then corresponding the velocity of sound is known in air, 340 meters per second or whatever it is. So this value, nx you choose one because they can only take integer values. So choose any one of them. What should be the dimension of the room? B you can find out. Let's say take this equals to 0. Then this equals to 1, this equals to 0. Then you find out this dimension because this is known, frequency is known. So 500 hertz, supposing, is a common frequency that is taken in case of auditoriums. Or you want to do it in 500, 1000. So several frequencies you can take, and correspondingly you can find out by choosing two of them 0, third one you can find out. Ny you can find out, right? And ny, if you choose 1, then b you can find out. Similarly, a you can find out. And combinations, diagonal, you can then check. Once you have found out the ABC, put each one of them 1, then the diagonal in the vertical one corner to the at the base level one corner, complete diagonal, 3D along the 3-dimensional, or put any one of them equals to 0, other two equals to 1, 1, then you get in the other plane, one given plane, what is the frequency, or for the same frequency is the resonance occurring. So using the formula you can simplify. There's no complication in this. Just use this formula, you can find out. And if you know the frequency, then and you know your A and B and C, right? Put this equals to 0, this equals to 0, you can find out whether resonance is occurring or not. For your C, put this equals to 1, or this combination. So using this formula, you can find out nx, ny, nz takes only integer values, 0, 1, 2, 3, etc. So usually you can try out with any one of these integer numbers, and combinations you can find out whether it's occurring or not. That's no more question? No more question. Yeah, any more question coming by? Any comment?
There were questions only. 2 questions.
Okay, no more questions. Fine. So what we can do is we can solve the problem to ourselves to help you out. We can solve a problem ourselves to help you out. Yeah. there must be a complete erasing option. Okay. Erase all.
Maybe what? We can use replace also.
But you can use
We can use separate type.
use a new code. Yeah, that's okay. So what is the problem that yes. Okay. Right. So it's the problem is a large rectangular hall of size 20 meter.
There is a question.
Yeah. What is it?
In your view, how a successful sound acoustic environment should be?
Okay. Where? We'll just ask the question back. Where? Which place? Within an enclosure? Where? Within an enclosure or where?
Or outside?
Yeah. Outside. Enclosure means is it auditorium, classroom? Where? Where is it? Which place? The acoustic environment. I mean,
In office place.
Okay, office place. Good. Now, office place, you see, office place, if you look at it, there are different types of office planning depending upon the type of offices. Say, if it is today, of course, you don't have cubicles of the kind that we used to have earlier. You have got all computer desks and things like that. Now, one issue is noise privacy. Noise privacy. If I am working, I don't want noise to come. So that's normally you have a barrier all around currently, and that leaves the noise privacy. So we don't want a noise level from other people who are in conversation to disturb you. So that's our general people. But supposing it is manager at a higher level who would be discussing about, like, is a personal manager or something like that, might discuss about somebody's career, promotion, or increment and things like that. They might need more privacy. So therefore, it depends upon. So essentially, or the order of around, because this is specified the maximum permissible noise level in such environment to be specified around 35 dB background noise, 40 dB. That should be quite enough. Is good. But noise privacy is very important because whatever I am speaking, it should not go to the next people also. So that's also an important issue in offices. And therefore, there are, of course, active systems which can capture what is the noise level and cancel and things like that. There are active systems, but generally passively, my noise, whatever I am saying, it should not go out. So one can design the office accordingly. In an open office plan, which used to be there earlier, no barrier, nothing, it is all open. So open office plan for drawing, drafting and similar sort of thing, earlier good old days. And nowadays, of course, everybody has got a computer, so AutoCAD and things like that. There the noise level, tolerable noise level should be general, tolerable 35, 45 dB or dBA or this order would be tolerable, acceptable. The other thing is that if it is landscape office, then it is mainly meant for sales and things like that. Each positions are or chair or things like that are placed haphazardly with maybe some trees and things like that. There also the general noise level should be order of around 35, 40 dB. But these are specified quiet or very quiet. If you remember, we talked about noise criteria card. NC criteria card sometime we have talked about. NC, according to NC criteria card, you can choose how quiet do you want. Right?
There is no question.
Any other question?
Any other question? You can start with us.
Yeah. So let's see. Let's look at one or two problems for helping you out in case you are doing. So you can. Can this be projected? Can this be projected?
ये शीट प्रोजेक्ट हो सकता है क्या इसको?
Can this problem be projected?
Yes sir, we are trying to email us. किसको मेल करना है? इसको शेयर करना है व्हाट्सएप पे। ये कैसे दिखता? अच्छा उसमें दिख जाएगा। व्हाट्सएप में तुमको ईमेल कर इसको।
Okay, right. So I think he'll just email you the problem, which says a large rectangular hall of size 20-meter long and 12-meter wide and 6.5-meter in height has a stage centered on 12-meter wall at one end. So you have something like 20-meter, right? 20-meter, 12-meter. So this is 20. This is 12. And there's a, six height, of course, is height is h is equals to 6.5 meter. Has a stage centered on the 12 meters. So somewhere here is the stage centered in this one. Right. The floor has a carpet covering laid on concrete. So there's a floor on which there's carpet. And absorption coefficient value is 0.37. So this absorption coefficient value is given. Alpha for the floor is given 0.37 for 1 K for 1 kilohertz, right? 1000 hertz frequency. The seating is upholstered leather cover seats with an absorption value of 0.61. So there are seats here, there will be sitting arrangement here, sitting arrangement here, etc. And they have 0.61 is the for the same frequency. It is 0.61 is alpha of the seats actually. Capacity is 210. So number of people, capacity is 210. Capacity of this space is 210. The side walls and the wall behind the stage is gypsum plaster. So this side is gypsum plaster, etc., etc. And which has got a coefficient of absorption coefficient of 0.04. There is a curtain over the rear wall. So there's a curtain here, the rear wall somewhere, right? Curtain over the rear wall, and absorption coefficient for the same is 0.75. Assume stage surface area is small compared to the rest of the area. The room is to be used for speech, and the specified reverberation is 0.9 seconds. So specified, RT is equals to 0.9 second, 0.9 second, right, for speech. What shall be absorption coefficient of the acoustic tiles, right? Planned to be used over the complete ceiling. So tiles will be used over complete ceiling. What is the absorption coefficient of those tiles, right? Okay, so essentially, what is Savine's formula? Savine's formula is, I think we use a notation RT. Yes, that's right. So TR, we are calling it TR or TR? Right, reverberation time, we are calling it as TR is equal to 0.16 B. Oh, right here. So a new page. Let me go to a next new page. 0.16 B divided by, so TR reverberation time is basically total absorption, or we would have written it total absorption, we would have written with S or alpha bar. So this is the total absorption. So for that, actually one of the alpha part is known. S alpha bar is basically equal to sum of Si alpha I. Now in this case, this will be for floor, wall, everything. So in case of floor area is how much? 20 into 12 and into 0.37. Plus for the walls, the total wall area you got to calculate out. How much is the wall area? Wall area would come out to be 12 into 6.5, and that's the vertical, and that should be one wall, two walls like that, plus 20 into 6.5. All right, and yeah, so this is two gypsum board we have written. Okay, this is only one, yeah, right, because, yeah, 12 into the other side. So this is 1. This will be 2, right. So these values are given and multiplied by 0.004, something like this. Plus the next line would be plus in addition to this. So this would be, well, that's right. Add here. So the walls, 2 walls you have taken. Backside there's a curtain and which has got a 0.75 absorption. So 0.12 into 6.5 into 0.75 plus what is there? The point seats were 210. Now normally for auditorium we take 2/3. If you take the full, then we'll take 210. Normally for auditorium design, one can take 2/3. So we take 2/3 multiplied by 210 into 0.61. So this also get added. And the last one remaining is the ceiling, which is 20 into 12 into the unknown alpha of the ceiling. And this value should be equals to 0.9. Now B of the room is known 20 into 12 into 6.5. 6.5. And if you put all these values, S, the alpha is the only unknown remaining. So 0.9 into all this, or 0.9 into alpha ceiling somewhere will come. You can form an equation. And if you solve for this, you get S alpha bar is equals to, okay, S alpha bar is equals to, right. So it comes out to be S alpha bar is, if I go to the next page, S alpha bar comes out to be 246.22 plus 240 is the area of 20 into 12 into alpha of the ceiling. That should be equals to into 0.9. So 246.22 plus 240 alpha C into 0.9 must be equals to 0.16 into 20 into 12 into 6.5. So only unknown is alpha C, and if you calculate out, it comes out to be 0.120. So calculate alpha C from this, it will come out to be 0.120. So that's the solution of this problem. It will help you if you are interested. You will find the solution of the problem of the similar kind. So which you have having assignments, and generally this gives you understanding how you use Savant's formula for related to how you use Savant's formula related to reverberation. Use Savant's formula for building.
Person is asking a basic book for acoustics. And
Well, there are a number of books actually, but I think I have given you some of them. There's a very good book by Jerome de Croom.
should we write it?
Is there in the reference that I have given in the original?
Jerome de Croom. Okay, I will write it here in the comments.
Yeah, Jerome J.D. Croom. Then there is a book by Foreman.
No need. मैं इधर लिख दूँगा comments.
Jerome D. Croom, J.D. Croom, Noise, People, and something like that. The building, book, we have given in the reference.
Yes,
J.D. Croom, we have given in the reference. And if you are looking qualitative things, if you are looking at qualitative things, number of books are there by this gentleman, particularly the fire book which I was using, the qualitative book. David Egan. David Egan has a very nice book on architectural acoustics. Acoustics, also qualitative. But if you are looking from some understanding physics of it, Croom has got a very good book, but it's very thick. And Foreman book is also good. But I have tried to take only 12 lectures out of this. You can have a course on acoustics. So I have tried to take only 12 lectures out of this. The equation that I have used mostly from either Croom, Foreman, and some of them are very basic. Like Savant's formula is very basic. You find in almost anything. So that's it. Trying to find out.
That was the second question also.
So, in case any quick question from you, I'd like to answer. Otherwise, we have just prepared one or two more some questions which will solve some problems. If you solve. Edit room, what is the noise, people, and something? What is the there are no references? References there? What's the name of the book?
Noise, building, and people.
Yeah, noise, building, and people. As I said, J.D. Kroon is a very good building. There's a book by Foreman.
Sound analysis
And noise control. That's by Foreman. Right? But everything I have not covered. I have covered only a small portion of these books. Whatever is relevant and can be covered around 10, 12 lectures, so that you have a first level of understanding. Now, supposing you want to go deep into it and research also, then it will be a lot of. It requires to understand a lot more, right? And it's a total physics. So, but David Egan's book, which I have not given in reference, is also a good book.
There is a question that what could be the solutions for absorptions and diffusions of light in office areas?
Okay. See, diffuse. Okay. Maybe I'll use this. See, diffusion. You want to diffuse the light. What is diffuse light? Artificial lighting. One of course is daylighting. If you look at it. So, if you are using daylighting, then use. So if you are using daylighting, the window is there. So essentially, use translucent one for it's in our country where we are from 8 degree to, as I said, 33 degree latitude, north latitude basically. Normally, north walls will not get any direct sunlight. Most of them, in these portions, you might get a little bit early in the morning and late in the evening, but most of the time you don't get late in the afternoon. Most of the time, so north side has to be, so they will get diffused light most of the time. So daylighting, diffused light you can use. If by chance there's a direct sunlight is also coming, then use the translucent surfaces which will bring in the diffused light only. The direct light it will block. It's not a transparent surface, but translucent. There must be a lot of these days available. But inside the office, you see, when you have a lamp, there are fittings. So fittings have polar curves. I think did we discuss? I'm not very sure whether I've discussed this part of artificial lighting. I think I would have. So diffused light will have 90% coming downward. This is your ceiling or suspension from the ceiling from where the lamp is coming. If the lamp is somewhere here, light will actually diffuse, direct light will come 90% downward, 10% only goes upward for direct fittings. And for diffused fitting, 50% will go upward, 50% will go downward. And you want to make it totally indirect, that's also possible, but you want diffused, completely diffused. So generally the globes, the diffuser are there, diffusing, is a fittings, which is a diffusing fitting, it can make it. So even if it's tube lamp, have a cover which is generally translucent, allows very little direct light, rather it will put in all diffuse light. So you the direct, you can avoid glares also straight away. So diffuse light means you have such fittings which will distribute the light. One of the ways is indirect lighting, completely put the lamp upward, then it will be reflected only from the ceiling and walls wherever it is going. So diffuse lighting, you can get it either by putting fittings which are diffusers, or using indirect lighting in the office. If you want completely indirect lighting is of course not good for office because you have to do some work. So diffusers can put translucent cover. There are fittings from almost many of will give you, if you look at GEC's table or Philips, there are ones which will be diffused kind of lamps and fittings available. So that's right.
Okay.
Okay, just see if there's that. One, I think we'll solve one more problem. Any questions so far? So
there will be a, because we tell them about the course that will be floated next semester also. Not yet.
that's doing it. But let's take another problem then quickly.
Second question.
Yeah. So there's another acoustics question he has put in. A source of a source of sound is 10 microwatt.
Please explain about cooling load factor in brief.
Cooling load
Factor.
uh, cooling load factor in connection with what? What is cooling load factor? Or is it the cooling load you want to know? What is cooling load? Because we didn't discuss about active system. So generally, we didn't discuss about the HVAC. All that we have discussed in this course is how to calculate out, let's say, amount of energy that is to be either withdrawn or amount of energy that is to be supplied. So the amount of energy that is to be withdrawn at a given point of time from the building, that's what we are calling as cooling load. But machine load will be different anyway, so that we are not talking about. So we are talking about the cooling load, hourly cooling load or hourly amount of energy that is to be withdrawn from the system. That's what we are calling as. So this is what it is. Now, how do you find it out? See, basically, at a given time instant, there's 656 component of heat transfer into the building. Number one, you have conduction heat transfer through the opaque surfaces, which if it is receiving radiation, then you must take the effect of radiation onto the external wall surface also, which will absorb some heat and transmit it later on. So one thing is through the conduction through the opaque body, because of temperature difference existing within the room and outside, and also because of the radiation falling onto those opaque surfaces. Now that is taken care of simply by UA into delta T, the steady part, and the unsteady part, if you look at it, it would be mu U A, temperature swing above the mean. If you have gone to that experiment, the equations, those are there. So physically, these are the two components. We look into if the temperatures are, divide the total heat conduction into two parts. One is the steady part, as if the mean is constant, inside and outside mean which are constant. So heat transfer due to the mean, and heat transfer due to any fluctuation above the mean outside, that we take care through a term called decrement factor, amplitude decrement, and its phase lag, time lag, how much later it will receive. And this you can also do for the radiation being received on opaque surfaces. Because radiation received now, it will come much later if it is fluctuation. Mean radiation, if I take it, so mean radiation, corresponding to that, there's a mean temperature rise outside. That would cause I can consider it to be constant and take the steady part of it. So we have divided into two parts in the method that I have discussed: steady and transient, and calculated separately. There are other methods, numerical methods like finite element, finite difference, or time domain response. We talked about frequency domain response. So physically, these two components, the conduction component. Then there's a component of direct gain to the glasses. So if a glass area, direct gain would occur. If the solar radiation is falling onto the glass, it will just get transmitted. And that we have talked in terms of AI theta, where theta is the solar gain factor. And then conduction through glass also you can take it. Conduction like as you take in case of opaque glass. Besides that, there are some heat transfer due to ventilation. There's some heat transfer due to ventilation, right? So ventilation heat transfer we take into account. It could be if the air changes are constant, then it is taken in a simple manner. If the air changes are varying, then hourly variation, there's another variable that's added, so you solve 25 by 25 metrics and all. But I'm not going to the metrics part of it, but I'm right now only talking to you related to physical way. So ventilation heat transfer can take place, and which would be, again, the air, that outside air comes in, it replaces some of the inside air, and it requires outside air at higher temperature. If it is at higher temperature, it will bring in some heat, because this will acquire the inside room temperature. So as it acquires the inside room temperature, that much heat will be absorbed by the room. So that has to be removed. So that adds to the cooling rate. So one is the conduction, direct radiation, and the ventilation heat transfer. Besides that, there are people, human beings, metabolic heat will be generated, that will cause casual heat gain, right? Also appliances. Supposing you have some sort of a kitchen, then it will be some sort of let's say a microwave, which consumes some amount of energy, or a heater. So these are casual heat gain. I think these are the major mode of heat transfer. So through this we calculate every hour how much is the heat that is required to be removed if I want to maintain a constant temperature. That's itself is the cooling rate. Did I leave any component out from there? So we have talked about conduction, two opaque body, transparent body, and then ventilation heat transfer, then direct gain, direct radiation coming in, and casual heat gain. Is there anything else? Is there anything else I just left out? I think that's all. That's all. So that's what is the cooling rate. Now, I have not really talked about any factor. I just told how to calculate this out, given the outside air temperature, design temperature is known to you, etc., etc. That's what it is. So I think if there is any specific factor you have in mind, just let me know. Take time.
What is thermodynamic W beating, wet bulb temperature? Thermodynamic.
Okay. I'm not very sure whether I did talk about that. You see, wet bulb temperature is a temperature. If I can calculate it out, right? By one is a measurement, which what you do in that case, you have a whirling hygrometer or some kind of hygrometer, where you find out, or it's a thermometer, its bulb is covered with wet gunny bag, or wet jute or whatever it is, and there's a depression. So depression from the dry bulb temperature. That is the wet bulb depression. Corresponding temperature, I call it wet bulb temperature, right? That's the measurement. Now when I'm saying thermodynamic wet bulb temperature, that is basically the one that you can calculate out theoretically. What is actually happening from the, the latent heat transfer is taking place. So it is in a saturated condition, surface is in a saturated condition, and at that condition, there will be a heat transfer. There will be, there will be a share it, yeah. So this is actually a diabatic situation. So basically, the heat will come to the bulb as H. Let's say area of the bulb is, or area of the surface is A, right, into TW minus TD minus TW, because dry bulb temperature will be always higher. So that will be H, if its convective heat transfer is taking place on the surface, right? So H is the convective heat transfer coefficient. That must be equals to latent heat multiplied by delta G, right? Latent is the amount of moisture evaporating from the same area. So I can, using this kind of an heat balance equation, I can find out TW in an adiabatic situation, right? So this is in joules per kg. This is the moisture changes, moisture evaporation taking. If I know the delta G change, moisture content changes, how much moisture content is changing. So then from that I can calculate out, if I can set, when I calculate this out, assuming an adiabatic condition, the wet bulb temperature I can calculate out, and that would be thermodynamic wet bulb. So is this equation all right? M into delta G. I do not know whether I have covered this in this course. I'm not very sure. Yeah, this is not. I didn't cover this, but anyway, this is. So this is in kilojoules or joules per kg. 2,501 we take actually. So joules per kg. That's for air. Sorry, I know latent heat of evaporation will take around 2,500. So 2,500 kilojoules per kg, and is the delta G is the amount of moisture change per unit volume, where, etc., etc. So when I write the heat balance equation, I can find out. That would be, assuming an adiabatic situation, I can find out the wet bulb temperature. That's actually thermodynamic wet bulb temperature.
Also about adiabatic saturation. What is adiabatic saturation?
Yeah. So that's actually, one should go into psychrometric chart. I can erase it off. First, let it be here. Let me erase this out. Erase this out. That gives you a better feeling, as if I'm working with the blackboard, right? so this is your psychrometric chart. This is the saturation curve. This is the zero. This line corresponds to, this side is your G, moisture content, or vapor pressure. Also you can express, this side is absolute, the simplest, and this side is dVT, and this line corresponds to 0% moisture content. This is saturation. So what is the question actually?
What is adiabatic saturation?
Yeah, adiabatic saturation would be, see, if I have, it's this temperature, this dry bulb temperature, this is the moisture content. So any point here would actually, within the psychrometric chart, the psychrometric chart is essentially a graph between these two. So any point here would represent the moisture content of the air and dry bulb temperature of the air. So adiabatic saturation would be that I am not supplying any heat from outside, right? And it goes towards this direction. It moves towards full saturation. So basically, what will happen if I am, if I am actually, basically, if I am supplying moisture, say in this case, in this temperature, I spray, let's say, water. Now this water will absorb such that it absorbs water from the air itself, absorbs, the air itself. So air temperature will go down, so dry bulb temperature will go down, but its moisture content will increase. So when it goes in this direction, and I reach this line where dry bulb temperature is reduced, but it has also reached a saturation point without any heat supplied from outside. For example, a desert cooler, if you are from North India, composite monsoon climate or hot dry desert climate, then people were using earlier what is called a desert cooler. Now that's a adiabatic situation where the dry air is blown by dry air is blown by some sort of a fan which will pull the air from outside, and there is a water spray. Water is actually sprayed through what you call khushkash, like very basically I do not know what the English word is, but it's a kind of a straw made board sort of thing through which water can percolate, drip down. So when the dry air comes in contact with the water, it absorbs the heat from, it loses some heat, and water it absorbs the water from the dripping down water, moisture vapor from the dripping down water, and its temperature gets reduced. So this is a purely adiabatic situation, and its temperature comes down, but its moisture content increases. And supposing I am able to achieve the saturation moisture, fully saturated, then it would be reaching that adiabatic saturation, right? Although I think this was not part of my course this time.
And somebody is asking that besides solution to the assignments, if you could give us some more worked out examples, maybe in the form of snapshot from any book, it would be of great help for me.
Well, the basic problem is there are no single book on the subject, and there are not problems. All these problems have been generated by me over last 20, 30 years, maybe one or two from books, but majority I have generated. So if we see if we can pass on some solved example, I'm not sure, but some questions we can pass on. Maybe we'll try to do that because I have a large question bank. So we'll like to pass on some example questions, some example questions, right? That I can do, which you can solve yourself. If you, after solving, if you find, or while solving, you find difficulties, you can just, communicate to us that this is where I got stuck. We'll actually solve also, give solution to you. So that's it. Because this level of this course, you see, there are books on acoustics, detailed books. There are books on energy efficient building design or energy, heat transfer in buildings. There are books on them, and there are books on some books on daylighting too, or lighting. But then when we have looked into, we try to make a kind of a first level course. I'll not say it's a second level course. It's first level course, but the physics is involved, so therefore slightly less descriptive, that is it. It's not a big deal at all, but it's a generally first level course trying to compile everything. So questions are not available really, readily available. Many of them I have formulated over the years myself. So we'll try to pass on some. Sure. Okay.
57 minutes have been completed. Okay, so would you please differentiate between short wave absorptivity and long wave emissivity?
Sure, I'll do that. You see, it's like this. Next page.
Okay, it's like I'm not sharing it.
Okay, now it's like this. You see, what happens is sun radiates at very high temperature, million degrees. So the spectrum of, if you see the spectrum, the solar radiation is from UV radiation, ultraviolet, to infrared, ultra UV to a large band, or the frequencies in which it radiates. And some of them are relatively, they can, since high energy, short wave actually. So the quality of the radiation is a function of temperature. So at that high temperature, sun radiates short wave. So this would be, the spectrum would be somewhere around, the visible is somewhere around 360 nanometer to 700 and something, nanometers and all that, right? Somewhere around that. Yeah. So beyond that also there is heat radiation. So that's what comes from sun. So sun's radiation, their wavelength is less and their short wave. Now the absorption and emissivity at a given wavelength, of course, is same for any body, but they are different for different wavelengths. So our terrestrial bodies, which absorbs the short wave radiation, gets heated up. The bodies in the earth, they absorb this radiation and gets heated up. Then they start radiating to elsewhere, which are at lower temperature, transmitting the heat to radiation to temperature. For example, in the night, in the outer cosmos, which is much cooler. Now, since the earth or earthly bodies radiate at much lower temperature, they actually radiate long wave radiation. So they are all heat radiation. You don't see the radiation going out from any hot surface. Many of this hot surface, you can feel the warmth of a wall sometime in summertime. Again, depending upon which wall it is, and you'll find that you can feel the heat but don't see the radiation. So that's not visible portion, but some infrared heat wave radiation. So at low temperature, the Earth, it emits long wave radiation. Now, long wave emissivity is important for us, so we'd like it to lose as much as. Long wave absorptivity will be similar values, but I'm not interested in that. While short wave absorptivity I'm interested in, the alpha value we denote by alpha, I don't want this absorptivity to be high. So if it's for a wall, if it is white colored, that has got a short wave absorptivity pretty low, could be of the order of around 0.4, but long wave emissivity of the order of 0.9 emissivity. So I am bothered about long wave emissivity, which should be high, and short wave absorptivity, which should be low. So this is the difference between the two. While radiating out, the earthly bodies all radiate long wave. While receiving the sun's radiation, it is all short wave. So that's it. Right? That's it.
एक घंटे का 1 आवर का क्या ड्यूरेशन तो हो गया है concluding comment.
Okay, so we have actually we finished our time. If you have specific questions and you are solving those problems and find specific questions, please do email to us. We'll try to answer them. But then questions like the industry, it is not used in industry. Well, it may not be. I'm not very sure. The academics cannot follow the industry. It's the other way around. So such question, it's all discussion. One can have debate on those, but I'm not interested in those ones. But if you have some questions, trying to solve and not able to, or trying to answer, do some assignments, not able to do it, please communicate to us. We'll do the needful and communicative back. We'll try to put in some questions. Did you note it down that somebody wanted some questions to be additional questions for solving? That will do. That will do. We'll put some snapshot. Right? That will do. So, any other question coming by?
No.
No, then thank you very much. Those 11 viewers, thank you very much for coming. And we'd like to answer all your queries. Thank you very much. As long as it is subject to it. Okay. Thank you.